Hello everybody and welcome to the whiteboard video for inductive propositions. The general plan for today is for me to explain in some measure these four relations. They come from throughout the file, so there's no perfect time to watch this video. I think it makes sense to watch certainly at least maybe the first half through EV and LE even before you've gone on to watch other videos, but I wouldn't want to watch maybe the latter half of the video about say ListNum and BT base until you'd seen those, because these I think will have the best punch if you sort of go through the exercise of trying to figure them out on your own first. So I'll warn you when we're about to get into later material, but I wanted to have a single video collecting all these ideas. Okay, how am I going to do it? My basic idea is I want to explain each of these in two steps. Step number one is translate them to implications. Step number two is translate them to inference rules, which we talk about in the text. And then maybe step number three is look at some derivations, which is a special kind of tree you can build out of inference rules. Okay, so let's get started. Here's EV. Let me copy that and move over to a little workspace down here. Okay, so EV. So the first thing we should do is translate these constructors which are, I also call them, evidence. Or you can even think of these as just, these are the primitive proofs of EV, right, the type we're defining. So there's two here. Let's write them both down. And really, it's just the types of them are theorems. EV0 is the theorem that the EV proposition holds for the number 0. I would read this as 0 is even. Okay, EVSS says for all n that's a nat, if n is even, then the successor of n is even. And I would read this as if n is even, then n plus 2 is even. Okay, I'm informally cheating if I write plus 2. We all know that S of n is not the same as plus n plus 2. That's 2 plus n. But okay, plus calm lets everybody relax. We all know what I'm talking about. Fine. Okay, so here I've just done the usual, like, let me translate this thing to a type. This presence of the for all here might be a little startling, or that I wrote a for all, but look, basically I need to talk about this n here and here, so I need to give it a name. So rather than just writing nat arrow ev what arrow ev s of what, I say for all n that's a nat, and then I can reference the natural number that I'm interested in talking about. So that's the general recipe here. Let's write it down. Oh, you gotta write all the letters. Okay, stick for all in front of every variable. Chain implications to conclusion. Right, so this is a variable, this is an implication, this is a conclusion. A better word for implication might be, oh, I don't know, premise. That's, I think, a better way to talk about it. Okay, so now we can ask, okay, what is true of EV? Well, what's true of EV is anything you can get by using these two constructors, right? That's these two, you just sort of apply them in a loop, right? Like, and that'll get you everything. So what do we know from that? It's like, well, we can come up with a bunch of basic proofs if we want. So EV0 is a proof that 0 is even. EVSS of, okay, give us a number 0, and then a proof that that number is even. Okay, EV0. That's a proof that EV2, right? Let's line this up. Can't do that on a real whiteboard. Okay, cool. So if that's a, oh, excuse me. Oh, right. Sorry for the screen flashing. So if this is a proof that 2 is even, then this should be a proof that 4 is even, right? And there's some stuff in the Coq where we talk about this. Okay, this is the bit of interpretation I was talking about where this was implications. So all this over here is EV0. Thank you, OBS, for warning me. Okay. Not sure if you can see that. OBS just warned me that I overloaded encoding. I think the screen moved too much. This poor laptop can't handle everything. Poor Sally Q whiteboard is having trouble. Okay, let's look at inference rules. So inference rules are just another way to present this same idea. So, so if this is part 1, this is part 2. So in inference rules, we would have 2 rules. So this is also written in the Coq. EV0. This is just a rule. Now, what goes in a rule? Let's draw it up here. There's a line, P1 through Pn are premises. And then C, okay, that's your conclusion. All of these are propositions. For all vars in Pi and C, P1 implies Pn implies C. This is the interpretation. What letter is that supposed to be? It's supposed to be a D. Right, so this rule reads as this interpretation. So here, basically, this reads as, hey, nothing, right, with no implications, no quantification, implies EV0, right? And this rule was called, oops, wrong color, was called EV_0. And I would call this kind of rule an axiom because it has no premises. That is to say, nothing above the line. Okay, that's EV0. What about EVSS? EVSS says, well, you can conclude EVS of S of n when you know EVn. And the way to read that is, if that, then that, and then we stick a for all. Right, so this is the same. The interpretation of this rule, EVSS, is the same as the interpretation of that utterance. Okay, so these are inference rules. This is just a different sort of diagrammatic presentation. Once you're used to inference rules, I think it's a lovely notation that sort of really concisely conveys the ideas that you want to give. But when you're not used to them, I would say it is, extremely annoying. Because it's just this like abstract lines on a page. The notation itself actually is really very old. One of the sort of oldest notations in logic. It goes back to Gottlob Frege, who not only had an extremely excellent name, but he sort of invented a lot of the formal notations we use for all of the logical work that we do, and did some really foundational work in thinking about logic in the mid-19th century. So, way to go, Gottlob. Okay, last thing I want to show, and I'll show it in some detail here, and then for the others I'm going to go through a little more quickly, is derivations. So here, right, like what we saw here, these are derivations by hand with explicit constructors. Right, we're just like building evidence, right? Now, what I like about inference rules in particular is that the notation you have here for these, like, the things above the line imply the things below the line, implies a sort of natural tree-like approach to talking about how any of these bits work. So let's see what I mean by that. So let's say we wanted to prove that EV4. Well, we might say EV4 via EVSS it suffices to show EV2. So now check for yourself, is this an application of the EVSS rule in some case? Well, yeah, we've instantiated n with 2, and so then this would be a valid bit of reasoning. Okay, but EV2, well, that by EVSS, it suffices to show EV0. And then EV0 we can find directly by EVO, EV0, forget the exact name. So the general idea is just like a tree or tower of instantiated inference rules where the leaves are axioms. Right? And this should make some sense in that, okay, if a rule has a premise of the same relation, it can't be the last thing to have a valid derivation. Right? The last thing, you have to close it out, has to be something with nothing above the line, or where the things above the line are not your same relation, right? It's something else that you can just have. Right? So it's worth pointing out that, like, okay, this one is valid. I love that they thought I just drew a pentagon when I was in fact drawing the letter D. If I wanted to erase, what would I do? No. What would I touch that one? That doesn't do what I wanted. Guys, you're killing me. Thank you. This one's a valid one. Let's look at an invalid one. Invalid. Okay, so what would an invalid derivation be? An invalid derivation is one where the rules are misapplied in some sense. So like EV3, oops, EV3, EV1, EV0. Right? What's bad here is right here, we have a bad application of EVSS. So that's one way to do it, is sort of say like, well, look, EV1 shouldn't have an EV0 above it, right? That doesn't make sense. Here's another one that's bad. EV4, EV2. So this one's bad because it's incomplete. Right? We don't know EV2, right? To know EV2, you have to build the tower further up. So these are the two ways that inference, that derivations can go wrong. Is you could apply something that isn't a rule, or you could misapply a rule or something, or you could just not complete your derivation, right? Like you just don't have it all there. Okay. So those are the critical concepts for being able to work with inference rules. What I want to do for these others is just go through each of them. Copy, please. I want to go through each of them and just draw up the inference rules for you. I think you can do the implications yourself. If you struggle with it, just holler on Zulip. I'm happy to help walk you through it. Okay, so I'm going to do LE next, and then I'll do list num and BT base. LE I'm going to give intuition for. I'm going to warn you before list num and BT base that this is like a spoiler alert kind of thing, and I'm going to try not to talk about them too much in any case. Okay, let's start with LE. So LE is the less than or equal to relation. So what are the inference rules we have here? What we have are two. There's LEN and LES. So when you're drawing them, you can just start out by saying, okay, look, I know I'm going to need these two. Let's do LEN first. So it says for all n is a nat, and then just LEN n. Oh, that's a little too close. Now, what do we do with this for all n is a nat? In an inference rule, you don't write the variables. The variables in an inference rule are implicitly universally quantified. So if you need to mention a variable in an inference rule, just mention it and we'll take it to mean a for all anyway. So we gave that here, right? This is the idea. So this is implicit universal quantification. Okay, so this is the whole of LEN. It is a, say it with me, axiom. And that's it. We're saying, hey, for any, so LE represents less than or equal to, for any number n, n is less than or equal to n. Okay. What about LES? Well, here we're saying if LE and M, let's do a different color. You go there. Then LENS of M. And again, we're going to leave all the variables off. So what does this mean? If N is less than or equal to M, then N is less than or equal to S of M. So this is not an axiom, but this is what one would simply call a rule. Now, an axiom, in my mind, is a kind of rule, if we want to be really specific. Okay, so great so far. Let's dig in a tiny bit deeper. LE is sort of an unfortunate name. I think you'll get more intuition out of it if we write it like this. N is less than or equal to N. N is less than or equal to 1 plus M if N is less than or equal to M. Right, so now I've written this in sort of a math notation, which is more familiar, and maybe this sort of seems a little clearer to you. Like, oh, right, these rules totally make sense. A good notation can make your life really easy. Okay, so just as practice real quick, let's do one last thing, and we'll move on to ListNum and BT base. How would you build a derivation that 3 was less than or equal to 6? Pause the video, see if you can do it on your own. Okay. What do we do? Well, we've really only got two tools in our tool belt, LES and LEN. LEN only applies when n equals n, and LES sort of lets us work backwards. Oh, I'm missing an M over here. Excuse me. Let's just work backwards. So if we applied LES, we would get 3 less than or equal to 5. If we did it again, we get 3 less than or equal to 4. If we did it one more time, we would get 3 less than or equal to 3. And then this we can have by the axiom LEN. Move that over. Okay. Hopefully you found the same. Hopefully that makes sense. If not, grab me on Zulip. Okay. If you have not yet watched the sort of mystery relation videos that follow this, videos like what, like 8, 9, 10, something like that. I forget the exact numbering. If you haven't watched those yet, maybe like hold off on watching this part, or you'll like spoil the surprise. Okay, let's quickly do this bit. Oop, undo. Okay, let's look at ListNum. So let's draw up the rules. There's 2 rules, ln nil and ln cons. Let me get, stop notifications. I didn't touch you and I don't want to hear about it. Thank you. Wow. I got the idea. Okay. We're not going to need that much line. Okay. Here's ln nil, and then here is ln cons. We're not going to need that much line in any case. Okay, what do we know? We know list num empty list 0, right? Another axiom. And then over here we know list num head cons tail S of n if we know list num tail n. Okay, if you haven't watched the video yet, I'm about to say what this relation does. So like I'm totally spoiling it. Okay, so this is computing length. How? Well, ln nil says the empty list gets 0. And then here, ln cons says that, well, okay, head cons onto tail. This h is universally quantified. We don't care what it is. We're just saying, look, if the tail relates to n, then head cons tail relates to s of n. And if empty list is 0, that means we can derive, for example, as follows. List num 1, 2, 3. And let me show you a trick. So like, let's say we don't know what goes here. Like we want to figure out what shows up in this position. Well, we know it's going to be s of something. Right? So we can just write a little blank there maybe. Okay, then what? Well, only ln cons could apply, so we're going to get something like list num 2, 3, something, and then these two will be the same, right? Well, now what could we find here? Well, this is going to need to be by ln cons again. So this is going to be s of something, so we can now write that little other s in there. And then we'll get list num 3 something. So as I'm building the relation, let me give myself a little more room here. A downside of these derivations being trees that go up, well, it's nice because it's botanically more correct, but it's frustrating because it's easy to run out of space. So if you're using paper, it's often helpful to start closer to the bottom of the page. Okay, so returning to this, what we're doing as we go is we just sort of are discovering the bits that we care about as we proceed. So I think that's like a really nice way to understand what's going on here. Let's finish it up. So list num 3 we got here via ln cons. Again, we can do one more ln cons, and now we'll get list num empty list something, and then this is a s of something, so that's going to be, we can sort of percolate these other s's through. Okay, and then well, what goes here? Well, now it's by ln nil. Ln nit? Ln nil, please. Too big. No. You go. You go. Excuse me. You go. And you go. And now we can fill in 0, 0, 0, 0. And that's 1, 2, 3. So, therefore, list num 1, 2, 3 is 3. Relates to 3. Okay, so that's why it's computing length. Okay, one last one in this too long video. BT base. I get you? Good. I'd like to go over here, please. Paste. Okay, this one's a little more complicated. Let's draw up the rules, though. What do we have? We have BT base B empty. And that's just called BB empty. Okay, what about the other rule, BB node? Well, we have BT base B node LVR when what? A couple of things. V should not be equal to B. And then we should have BT base BL and BT base BR. So we can kind of draw the connections here. Right, and then we're leaving off all these other variables because they're just universally quantified. Okay. Okay, so this is interesting because this is the first time we really see multiple premises. You can also say premises, whatever feels natural to you. It's great. Okay, so either of these is great. Now, let's look at a derivation of this. So let's build one for. Can I see everything? There we go. BT base C node. I'm just going to use some here, maybe I'll just draw the tree. That'll be a little easier. C, and then my tree will be G, T, A, T. I don't know. Great. Okay, so I'm just going to draw it that way. Use that tree notation. Should be a little easier for us. Okay, so what do we need? So we would need here what? C not equal to G, and we would need to find BT base C T. I'll just draw the little empty things, because that's a leaf. And then we would also need BT base C A T. Okay, so now what's interesting is now there's two subderivations, right? We need one for here and we need one for here. This is what's called a side condition. Okay, let's do these subderivations. Now here for BT base CT, we would just need C is not equal to T, and we need BT base C empty, and then another BT base C empty for each of the two children, and we have those both immediately by BB empty. Okay, let's give ourselves a lot more room because we've been running low. Okay, so here we're going to need C not equal to A. We're going to need BT base T blah blah, and then BT base, C T blah blah, and then over here we'll need BT base C empty. This we find immediately by BB nil. And here we're going to have the same derivation, right? Like all of this could go here. I'll just redo it once because I did it kind of sloppily over there. So here we just need T is not equal to A, and BT base C empty for the left child, right? Down here there's a sort of empty, right? We got to cover it there. And then we'll need another one for the right child. Oops, wrong color. So at this point you can kind of see, well, what's this doing? Spoiler alert. What's this doing? Well, it's kind of hunting through the tree to make sure there are no C's in it, right? That's what's going on here. One thing I think I've very neatly demonstrated, or I should say sloppily demonstrated, it's hard to plan exactly where your derivation is going. So it makes sense to start with a big, clean piece of paper and be willing to sort of like maybe draw it over or be more careful. You can see that the second time I did the derivation for this leaf T, it was much neater than the first time I did the derivation for the leaf T. That's totally ordinary, and I think that it gets better with practice. But I've had tons of practice, and look what I did. So be a little forgiving on yourself. Okay, that's everything I wanted to talk about. This was a very long video. I think it may pay for you to sort of jump around. Sort of like don't feel like you need to get everything in here completely on your first time. You can mix it up. Okay, that's it for now. Talk to y'all soon.